Hey guys, it's Mr. Brengle, and today I'm going to be going over the virtual electricity lab with the circuit building. So the first sheet that you have here is your simple circuit. And if we go back to our instructions here, it says add the potential difference of the battery and the bulb, enter the result in the spreadsheet, sum of the potential. So clicking back over here, you guys can you can see that in the battery here is 9 volts, and the bulb, when you measured it with the voltmeter, was negative 9 volts. So the sum of the potential is 0, and that is it's supposed to be like that because of this rule right here, the loop rule. So let's just hop on over here to Google and look at what the loop rule is. So Kirchhoff's loop rule states that the sum of the voltage differences across all of the circuit elements must be 0. And you can see here that 9 plus negative 9 is 0. Okay, so that is the loop rule. It always has to go down to 0. Voltage is essentially pressure that pushes the current or the electrons through the circuit, and we have to get back to 0 by the time it gets around to the battery each time. All right, so let's go ahead and move on to the series circuit here. The first step, it says find the total resistance in the circuit, and to do this we just need to add the resistances of each of the resistors. And this is very simple for a series circuit, so I'm going to say RS for series resistance is equal to all of the resistances added up. And that could continue on. So for our purposes here, our total resistance in this series circuit is equal to 10 ohms plus 15 ohms plus 20 ohms. So the resistance in the series circuit here is going to be 45 ohms. And we can see that over here that we take the 10, the 15, the 20, add them up, and it becomes 45. Now moving back, number 2, to find the total current in the series circuit, you should not need to do any math. If you notice, there's a trend in each of the resistors. Just enter the value in the total current box that goes along with the pattern you see. There's a rule for this result called the Junction Rule. So if you follow my cursor here and see the current in each of those bulbs, if you measure the current across each of those bulbs, it was always 0.2. Well, let's go look at the junction rule here. So Kirchhoff's junction rule states that any junction or node in an electrical circuit, the sum of the currents flowing into that junction must be equal to the sum of the currents flowing out of that junction. So with a series circuit, the current only has one path to travel through. In fact, let me go back over here to the board, and I'll kind of draw this out for you. So if you have a battery and a circuit, and here, let's say here's a light bulb, and here's a light bulb, comes around here, and here's a light bulb. Okay, we'll use, let's say the electrons are moving. The electrons are moving this direction. Well, they have to go through this light bulb, right? And then they're going to travel around this way, and they have to go through this light bulb. And it has to go through this light bulb, and then it comes back around here. So the total current in that circuit should never change, right? The junction here that we're talking about would be essentially at the battery, and so the current that goes out this way has to be equal to the current that comes in on the other side. So the current in a series circuit never changes. It's always the same. So that's why we have this down here. The series rule for current is the junction rule, which means that it's going to be the same. So the total current over here is going to be equal to the current at any point in a series circuit. Does not matter where you measure it, it will always be the same as the total. Moving on here to number 3, it says to find the total voltage in a circuit, add the battery voltage of bulb with the 10 voltage or the 10 volts, the bulb 15 and bulb 20. This total is a result of the loop rule again. So if we come over here, if you guys measured your voltage correctly, which you should have the red lead on the left and the black lead on the right of the light bulbs, you would find that the voltage drop in bulb 10 is -2, -3 in the 15 ohm bulb, and in the 20 ohm bulb it's -4. Well, if you add those up, it comes out to be -9. And remember, the loop rule stated that the sum of the voltage differences across the circuit must be 0. So this should make sense. These three right here need to add up to be -9 so that when it's added with the battery voltage, it goes down to 0. Okay, so I apologize. Number 4 here, the rule for current in the resistors should be the same. Do you see why? Enter same in the box next to the rule for current. So we already did that. We talked about this right here. The current rule. Okay, and the rule for potential in the resistors is adds. Do you see why? So looking at this, the loop rule and adds, you can see that in the potential difference or the voltage. That's the same. That means the same thing. Potential difference in voltage. That these have to add up to the same to subtract entirely from the battery. So we've already talked about that. All right, let's move on to the parallel circuit now. So finding the resistance in a parallel circuit is different than finding the resistance in a series circuit. There's a different equation which we do have listed right here underneath this circuit, but we'll go ahead and do the math together. So if I'm looking at a parallel circuit, one over the total resistance, and I'm going to put RP here for parallel, is equal to 1 over R1 plus 1 over the second resistor plus 1 over the third, and etc. So for our circuit, 1 over RP would be equal to 1 over 10 ohms plus 1 over 15 ohms plus 1 over 20 ohms. When you do this, 1 over RP is going to come out to be 0.216 repeating. Now just be careful, because a lot of people will enter 0.26 or 216 as the parallel resistance, but this is 1 over RP, so to fully solve for this, the parallel resistance is going to be equal to 1 divided by 0.216 repeating. And when you do that, you are going to get 4.62 ohms of total resistance in the parallel circuit. So if we go back to our lab over here, you can see that I've put the total resistance in here is 4.62, and I just want to point out that the total resistance in the parallel circuit that has the same resistance values in those light bulbs is actually much less than the total resistance in the series circuit. And the reason for that is because if we go back over here and I were to draw a parallel circuit, so I'll just kind of draw it right here. Okay, in the parallel circuit we have branches, right? So the electrons are traveling, say the electrons are traveling this way. When they get to this point, they can either go through this branch or they continue this way. When they get to this point, they go through this branch or they continue this way. The point here is that when the electrons go through a branch, so like if they go through this first branch right here, they are only going to travel through this light bulb right here. Okay? They're going to go this way. And then the electrons that go up to this point right here are only going to go through this light bulb, and they will travel back down this way, and then they'll join up down here with the red dots. Okay, and the same thing if electrons go through this branch up here, they're only going to go through that top light bulb, and then they'll travel back down and go to the battery. Okay, so the point here is that by providing branches, we are actually decreasing the resistance. It's providing extra pathways for the electrons to travel through, which makes it easier for the electrons to travel. Okay, so let's go back over here now. We've done the total resistance. It says to find the total current, simply add the current of each resistor together, enter your answer on the spreadsheet. So if you were to measure the current at each of those bulbs, you would have found that at the 10 ohm bulb it was 0.9 amps, at the 15 ohm bulb 0.6, and 0.45 at the 20 ohm bulb. Well, if you add all of those up together, it comes out to be 1.95 amps. So you can see up here that I just entered an equation, the sum of all three of these, to get the current right there. And so if we look at the parallel rule for current, it is that junction rule, and it's that they add up together. Now this is different from the series circuit, because in the series circuit the current is the same everywhere, right? It's the same everywhere. But in the parallel circuit, we have to consider the current in each branch, because remember that in each branch of this circuit here, right, this would be branch 1, branch 2, and branch 3, we have a different resistance in each branch. So the current should be different in each branch. Okay. Now, the total voltage in parallel follows a rule similar to the total current in series. Just enter a value in the total voltage box that goes along with the pattern that you see. This is the loop rule again. Okay, so the pattern that you should have seen here is that every single branch had a voltage drop of 9 volts. And this is much different than the series circuit where they added up to 9. Now in the parallel circuit, each one is 9. So the thing here is that we're not going to add these up. Okay, they're all going to be the same. It's very similar to, like it mentioned before, the current, right? The rule over here for current, it's the same everywhere in the circuit, and it's the same deal for parallel, but with voltage. The voltage drop is going to be the same in each branch. Now, the way that you need to think about this is that each one of these branches in this parallel circuit here, branch 1, 2, and 3, has a light bulb. And we can think about these as almost individual series circuits, because the electrons that go through branch 1 do not go through the other branches. So if we have a 9-volt battery, that means that at each one of these light bulbs, 1, 2, and 3, we must drop that 9 volts. Okay, because when we get past this light bulb right here, we have to go back down to 0 but when we get back to the battery, right? We can't have extra voltage. So again, if I have 9 volts going into this second one right here, I have to leave with 0 volts because it's got to get back to the battery with 0 volts. Okay, so the rule there is that it is the same. Let's go ahead and move on. The rule for current in the resistor should be adds. Do you see why? Same for the voltage. We just talked about that. So again, this all adds up to the total current, and then it's the same over here. Now, one thing that I'll go back and say about the total current, if you were to measure the current at one of two places, so anywhere over here or anywhere over here before or after the last branch, these values for current would be the total current, all right? Because the current is adding up once it gets to this point here. All of the currents from all the branches are combining. So this would be the total. And then over here, it would also be the total because it has not, the electrons have not gone on to those individual branches yet. Once they hit a branch, then we would get individual currents on all those branches. Okay, so now the combo circuit. And the combo circuit can be a little tricky, but we'll do lots of practice with it. So this one has a series and a parallel part. So it says first add the 15 and 20 ohm resistors to the parallel resistance example we used in the parallel circuit. Enter the final value in the green box. So for this one, what we need to do is we're going to look at this real quick. Let's go over to the combo circuit. So the blue one right here is showing that bulb 10 is in series, basically. And then bulbs 15 and 20 are in parallel. So let me come over here and let's draw this out. In fact, let's just make a new page here. And so let's say, so the battery's here. And let's say the first bulb is right there. And then we go up here, and then there's a branch, and there's a bulb here, and a bulb here. Okay. So this would be the 10 ohm bulb, this would be the 15 ohm, and this would be the 20 ohm bulb. Okay. So basically what's going on here is the electrons are going to leave this battery, and they have to travel through the 10 ohm light bulb, and that's why that one is in series. It has to go through that. But when the electrons get to this point right here, they essentially have a choice. They can go this way or they can go this way, and that's completely dependent on the resistance. Now, the electrons are going to prefer to go through the path of least resistance, so they will go on the 15 ohm light bulb first, but once that branch gets filled up to the max with electrons, then they will start going through the 20 ohm resistor. Now this happens so fast you're not going to see it, like it's not going to go through the top and then after a little while it fills up and then it goes through the bottom. This is essentially instantaneous. So when the electrons travel through the 15 ohm resistor, they're going to come around and then they will meet up with the electrons that travel through the 20 ohm resistor over here, and then they go back around to the battery. Okay, so what we want to do here to solve for the resistance, the total resistance in this circuit is going to be equal to the resistance of the parallel portion plus the resistance of the series portion. Okay, now to do this we first need to find the parallel resistance, so let's do that first. So 1 over RP is equal to 1 over 15 plus 1 over 20. 1 over RP is equal to 0.116 repeating. Don't forget that we need to rearrange this. RP is equal to 1 over 0.116 repeating. And that is going to be equal to 8.57 ohms. Okay, so that is our parallel resistance. So we'll go back over here to right here, the total parallel resistance. I've plugged in 8.57 in that green box. And now, after that, it says next add the 10 ohm resistor and the parallel resistance together into the yellow box. That's the total resistance of the current. So that's what I've done here is I basically added the 10 and the 8.57, and that gives me 18.57. So going back to math over here, what we've done is we took this value, which we solved for right here, and then this in the series, that's just this 10 ohms right here. So now the total resistance is equal to the 8.57 that we got for the parallel resistance plus the 10 ohms that's in series that the electrons have to go through no matter what. So when we do that, it becomes 18.57 ohms. All right. Last part here, to find the total current in the circuit, take the battery voltage in the aqua blue box and divide it by the total circuit resistance in the yellow box. So that's what I've done down here, the total current down here. You can see I entered an equation that takes B2, which is the total voltage, and I've divided that by the total resistance. So just for our purposes here, let's go ahead and show that the total current is equal to the total voltage divided by the total resistance. This is an equation that you're going to see quite a bit. We call this Ohm's law, and we will talk about this in detail later. But essentially, you may have seen this equation like this, V equals IR. Okay, so we can rearrange that obviously for each of those variables, but this is Ohm's law right here, so that's what we just did. get this number here, the 0.485. The last thing, finally, to find the total voltage, add the battery voltage, the voltage of the 10 ohm bulb, and either the 15 or 20 ohm bulb voltage. Now the reason that we do that is because you can see right here that the voltage drop in the 10 ohm bulb was negative 4.85. Well, we know that the voltage drop has to add up to be negative 9 to balance out the battery. So that means that the voltage within the parallel circuit must be negative 4.15, right? Because that's what it would take to get all the way up to 9. And just remember that the voltage drop is going to be the same in a parallel situation. So 15 and the 20 ohm bulbs are in parallel, so the voltage there will be the same. And we're not going to add these up, just like we did back here in the parallel circuit. Remember, all three of these were negative 9, but we only really need to look at one of them because each of those branches is like an individual series circuit. Okay, so this is a crash course in series, parallel, and combo circuits. We'll keep working on them in class.